What is up, you guys? Welcome to another lecture of this series entitled Machine Learning with TensorFlow and Scikit-learn. In lecture number 7, we're going to talk about linear regression. And today is a bit different because I've got a guest, as I'm always convinced that having multiple perspectives about a certain topic is way off better than, just one person's point of view, right? So that's why I've brought over Lewis, and Lewis is the channel owner of What is Artificial Intelligence. You can go ahead and search him on YouTube. He's got good stuff on artificial intelligence, on AI. So also Lewis in his channel, What is Artificial Intelligence, talks about supervised learning along with semi-supervised and unsupervised learning, as well as clustering, backpropagation, neural networks as well, and many of its applications such as natural language processing, object detection, image segmentation and computer vision, Turing test, many good algorithms on his channel really, such as the genetic algorithm, and many of real life applications like the transformer networks that shows how Google Translate works. So please help me in welcoming Lewis on the channel. So, Lewis, how you've been? How are you doing?
I'm doing well. Thank you for inviting me on your channel. And how have you been?
I'm great. So, can you walk us through what linear regression is? Why should, everyone in machine learning know it? And is it also found in other domains as well?
First off, linear regression is an algorithm that every machine learning enthusiast must know, and it is also a good place to start. As you know, it initially comes from statistics.
Right.
It is a technique studied to understand the relationship between two variables by setting a linear equation.
Okay.
In applied machine learning, we borrow a lot of algorithms from many different fields, including statistics, and use them towards our goal of minimizing the error of our model, or making the most accurate prediction possible. You can see how statistics are very useful in machine learning.
Right.
Since we never have a definitive 100% sure answer, it's always uncertain, optimizing our confidence by minimizing the error of the model, which is where statistics comes in handy. If we dive deeper into linear regression, we will see that the most basic form has two variables, the dependent variable y and the independent variable x. You can see it as the equation of a line, which is y equals mx plus b, where x is the variable you will like to have the equivalent y result, using a slope, m, and a y-intercept, b, found from a line representing your data points. In short, the slope decides the rotation of the line, and the intercept decides its translation. So, if your data points follow a linear pattern, like this, you will be able to find those two variables to predict how a dependent y variable is affected in relation with an independent x variable. You can then use linear regression in a way to represent this relation we already know from our examples to forecast new observations. Of course, all your data points won't be exactly on the line, but by calculating the distance error between your points and the line, you will find the best fit with the lowest total error, which will be your final line. Which is where your machine learning minimization algorithm will come in play.
Okay.
Finally, given the representation is a linear equation, making predictions is as simple as solving the equation for a specific set of inputs.
Right.
With just an x value, you will be able to quickly find the corresponding y value by simply solving the equation. Finally, in machine learning, we often do regression in a multidimensional form. But don't be afraid of this.
Okay.
It works the exact same way as it does in 2 dimensions, finding a relation between all the variables to predict a future observation.
Perfect. That was some good explanation. So what I understand from you is that linear regression is sort of a linear way of performing prediction, right? Given some data. So it's a type of supervised linear way of prediction. I'm just wondering, do you have any examples, like where could this be applied?
As I explained previously, linear regression is used to understand the relationship between two variables. This way, If you'd like to know how an increase in the gross domestic product, GDP, of a country has an effect on the life satisfaction of its citizen, using linear regression could be a great and simple way to get an answer. For example, let's use this graph taken from a study made in European Union by researchers at Vilnius University using data from 2008. It shows the life satisfaction taken as a country's percentage of respondents saying they are very satisfied or fairly satisfied with the life they lead, versus the GDP per capita of those countries. Just by visualizing this graph, you may already see that it looks like it follows a line which will look like this. From Bulgaria to Sweden, where the increase in GDP per capita clearly increases the life satisfaction of its citizen.
Right.
The line will be calculated by measuring the minimum distance between the points in order to find the most optimal line, which will look like this one. Then, if we add a new observation, say we have France which had a GDP per capita of around 27,000 euro in 2008, you will have a life satisfaction resulting of around 80%, which is most likely probable. In short, linear regression helps you find the relation between multiple variables based on the simple equation of a line.
Okay. Thank you, Lewis, for being a guest on my channel. Indeed, you gave us many insights on linear regression. Make sure to subscribe to Lewis's channel. It's called What is Artificial Intelligence? And I'll take it from here. Okay, so we've treated machine learning models, to be more specific, classification models, and their corresponding training algorithms, mostly like black boxes. However, having a good understanding of how things work under the hood can help you quickly target an appropriate model. The right training algorithm to use and a good set of hyperparameters for your task. Now, understanding what's happening beneath the hood will also help you debug issues and perform error analysis more efficient. Lastly, most of the topics that we will be discussing that fall in the category of linear models will essentially lie in understanding, building and training neural networks, as we will see in future lectures. Now, in the coming few lectures that have to deal with linear models, we will start by looking at linear regression models, one of the simplest linear models that exist. We will then discuss two very different ways to train it. First one has to do with closed form equations that directly computes the model parameters that best fit the linear model to train the training set, whereas the other one is iterative, and it is based on iterative optimization. One iterative algorithm that performs minimization of a dedicated cost function is called the gradient descent, that gradually tweaks the model parameters to minimize the cost function over the training set, eventually converging to the same set of parameters as the first closed form approach. We will also take a look at a few variants of gradient descent that we will use again and again when we dig deeper into machine learning and study neural networks. That is, we'll also be taking a look at batch gradient descent as well as mini-batch and stochastic gradient descent. Now, even though a few coming lectures fall under the category of linear models, we will also take a look at polynomial regression. That is a more complex model that can fit nonlinear dataset. Since the model has more parameters embedded than that of linear regression, it is more prone to overfitting the training data. So we will look at how to detect whether or not this is the case using learning curves. Then we will look at several regularization techniques that can reduce the risk of overfitting the training set. Last but not least, we will also take a look at two important and most commonly used models for classification tasks that are termed logistic and the softmax regression. When we were introducing machine learning, we gave a simple regression model when talking about life satisfaction. That is, life satisfaction is a linear function of GDP. And theta 0 and theta 1 are referred to as model parameters. More generally, a linear model makes a prediction by simply computing a weighted sum of the input features, plus a constant that is termed the bias term, also called the intercept term. Now in calculus, this is the y-intercept, right? Because while setting x or theta 1 to 0, your y is simply theta 0. right? So generally speaking, a linear regression model assumes the following. So you'd predict a y hat based upon the following weighted sum, where y hat is referred to as the predicted value, n will be the number of features, and the x's are referred to as feature values. So x1 is the first feature value, x2 is the second, and xn is the last feature value. Whereas the thetas are referred to as model parameters, right? Now, this model, if you come and just take a look at it, it looks pretty messed up, right? Because you have a sum and you're expressing each and every term as a expanded sum. So you can actually write this as the sum of theta k xk, that is theta transpose x, where theta contains all the values theta I, so theta 0, theta 1, theta 2, down to theta n, right? And so does x. Notice that the first entry of x is 1 because theta 0 is multiplied by a 1, right? So in other words, x0 is always 1. We will be referring to the vector theta as the parameter vector because it contains all the model parameters, including the bias term theta 0. Also, we will be referring to x as a feature vector because it contains all the feature values with 1 in the first entry. Now, you might find in some references that people prefer to call this theta transpose x as h of x, where h is h sub theta. And why is that? It's because h sub theta is the hypothesis function using the model parameters theta. So this is just a hypothesis and you're the one who's testing a linear model. Thus, you're the one who assumes that the model is behaving linearly with model parameters, and hence the name of the function h of theta, that is the hypothesis function using the model parameters theta. Okay, so that's the linear regression model. So now the question is, how do we train it, right? Now, remember that training a model means setting its parameters so that the model best fits the training set, right? For this purpose, we first need a measure of how well or bad the model fits the training data. Now, a common performance measure for regression models is the RMSE, that is the root mean square error. Therefore, to train a linear model, you need to find the best theta that minimizes the RMSE. Now, in practice, it is simpler to just, instead of minimizing the root mean square error, you just minimize the mean square error. So root mean square error is just square root of the mean square error. So you could simply just see that if you're minimizing RMSE, then it's equivalent of minimizing the MSE, right? And thus the theta that minimizes RMSE is the same with that minimizes the MSE, because the value that minimizes a function also minimizes its square root. Now, so just before writing the definition of the MSE, it's worth noting that in the training set, all the feature vectors are stacked into one matrix. So the training set X is actually a matrix where all feature vectors are stacked in its rows, right? So denoting X superscript 1 as the first feature vector. Well, we're going to have to take the transpose of that because we're assuming all the feature vectors are actually column vectors. So stacking it in the row, you have to perform a transpose. So as you can see, given m feature vectors, we stack them in the rows of X as such. And likewise, it will turn out to be useful to define all the target values that are the Y's, right? So a vector Y contains all the targets Y1, Y2, down to... Now actually, for notation's sake, since we denoted the feature index as a superscript in the X vectors, I'm going to do the same thing for the Y's. So Y1, where in this case it's a scalar, it's not a vector. Y2 down to Ym, right? Okay, so now that we have defined where again Y is referred to as vector of target values. So now we can write down the MSE as the mean squared error, right? Because really that's what you're doing. You're taking the mean of the squared of errors, right? Each of the feature has a corresponding target value. So you're measuring the output of feature xi, that is supposed to be yi hat, right? Y hat, which is of course not necessarily yi, right? And this residual or difference is the error, and that's it, mean square error. RMSE just further takes the square root of all this quantity. So now, to find the value theta that minimizes the MSE cost function, there is a closed form solution for that. In other words, we have an equation that given x and y, you can get theta, referred to as the normal equation, and it is the following. Now this actually has a very straightforward proof which I'm not going to show in this lecture. However, if you're interested in seeing the proof of deriving the following least square estimator, or the theta that minimizes the MSE, just leave a comment down in the comment section below, and if I see a lot of requests based on normal equations, then I will definitely throw out a 5-minute video explaining step by step how we can derive this. Okay, so yeah, given your training set and your target values, you can straight ahead go and just do this simple calculation to get your theta hat. That is the theta that minimizes the error between predicted and actual values, target values. Now let's see what we can do with this on Python. So let's first of all import NumPy, right? And let's generate some x values. That is some random values as such, right? And their corresponding y values according to the equation y equal 4 plus 3x, right? Of course, with some random noise, right? Now let's plot y versus x to see what type of data points we can visualize. I'm going to need the matplotlib, and I might be using in the future the MPL, the matplotlib as a package, so I'll call it MPL. Okay, so this is how I wanted them to be in dotted points, so as such, right? Let's label the x-axis, it's 1, enlarge the font size, right? Label the y-axis, but let's rotate this guy, right? Okay, good. Now let's try to compute theta hat using the normal equation. First, notice that the x feature vector has 1 in its first entry. So a way to incorporate this here is by concatenating a vector of all 1s along with the x, because x doesn't have 1s in its first column, right? So this is what we're doing. Taking a look at xb, here you go. Okay, next, notice that in this equation we've got x transpose times x. So let's compute that. X underscore b dot t, which stands for transpose, dot xb means times matrix multiplication. Then we're going to take the inverse as such. So using the linear algebra package in NumPy, we're calling the inverse function. Then you'd want to multiply all this matrix by x transpose. So dot x underscore b transpose. And finally, you'd multiply all this guy by the y, right? So dot y. And there you go. The first entry is your theta 0, and your second one is theta 1. So there you go. Now, ideally, you'd want to see that this guy is a 4 because of what we generated. So theta 0 is actually 4 and theta 1 is actually 3, right? However, this fit gave us a very close estimate, that is 4.59 and 2.93, right? So we can say that given this model, we got the following. Now you can make predictions based off theta hat, right? So the way you can do this is, let's call x new, that is an array containing 0.0 and 0.2, right? So x new looks like this. So it's an array of 0 and 2, and we're going to add 1s as we did previously, right? So x new b looks like this, 1s here, and the points are in the second column. And last but not least, the prediction is done as simple as this equation. So we're going to grab our theta, which is computed here. So I'll call this theta best fit or best, and I'll have to transpose, then multiply or perform an inner product with my x new b. But the best is not defined. Well, let's run this again so that it's defined. There you go. We saw that zero's predicted value would be 4.59 and 2 would be 10.46. Now let's plot the model's prediction as follows along with the training set. Let's limit the axis. Okay, good. Twice, let's label the x and y axis. Right, there you go. So what we just did is wrote from scratch or using only NumPy other than matplotlib, which does the plotting. Well, we use NumPy to write from scratch the normal equation. Actually, this is what scikit-learn does beneath the hood. So if you're using the sklearn module, then you'd want to import the linear model, and from linear model you'd want to import linear regression. Call initialize a linear regression object, right? Then perform a fit on y versus x, and last but not least you'd want the coefficients, right? Run. So 4.59 and 2.93, as you can see here, 4.59 and 2.93. So the same exact equation is used by sklearn because that's what linear regression is, right? And now let's use sklearn to predict some given values. So I'll call in predict facet x new. So instead of us having to perform this inner product and also having to insert a column of all ones, you can just perform the predict function by linear regression found in sklearn linear models. So running this, and you get a 4.59 and a 10.46 as we got over here. Okay, now let's talk about the computational complexity of actually, computing this normal equation over here. So as you can see, the normal equation requires x transpose x inverse. So this guy over here, which is an n by n matrix, right? Actually, it's n plus 1 by n plus 1 because x right here, okay, you've got m rows, but how many columns do you have? You've got m by n plus 1 entries. So m rows and n plus 1 columns. Why n plus 1? Because x contains 1 right here and then n entries. So 1 comes from here, and then you've got n entries right over here. So in total, you've got n plus 1 entries, right? So back here, x transpose x is n plus 1 by n plus 1, right? The computational complexity of inverting such a matrix is typically got many algorithms to compute matrix inverse, right? From Jacobi, you can also implement a Newton type algorithm, many algorithms in the numerical linear algebra literature. But more or less all of them require somewhere around O and 2.4. What does that mean? It requires almost that much flops or operations to compute this inverse right here, n to the power 2.4. Now you find papers in the literature that is plus or minus epsilon of this order. Okay, and maximally, so the range is 2.4 till 3, right? Anything above that is too slow, and anything beyond that is very fast, if you can find something beyond that, right? Now for specific structures, if your matrix is, let's say, upper triangular, you can save a lot of operations. It's really structure dependent if you find anything below that, right? Now in the extreme case, when it's diagonal, all you have to do is just perform an inverse of the diagonal entries. So that will boil down to probably ON, right? Now going back here in the general case, if you double the number of features every time you double, so what does that mean? For you as a machine learning or AI engineer, what does that mean? Or even a data scientist, what does that mean? It means every time you double the number of features, you multiply the computation by roughly something like, if you're using n to the power 2.4, then let's say 2n to the power 2.4 would be 2 to the power 2.4 n 2.4, right? Which is somewhere around 2 to the power 2.4 is something 5 so multiplied by What does that mean? It means every time you double the number of features, you're multiplying the computational time by roughly 5.2. And if your algorithm takes on cubed, then you'd multiply by 2 cubed, that is 8. So from 5.2 till 8. So every time you double the number of features, the computational complexity rises exponentially, order 2.4 till 3, right? Which means that the normal equation gets very slow when the number of features grows large. So imagine n is about 100,000 features. You might wait 24 hours for this matrix inversion, right? On the positive side, this equation is linear with regards to the number of instances in the training set, that is OM. Right? So it handles large training sets efficiently. So if you've got a lot of feature vectors and a low number of model parameters, this is good. So n is low, m is high, no problem, right? Because as you can see here, you've got an x transpose y, and you know, this is just, there's no inversion. This is linear. This scales linearly because all you're doing is multiplying then adding, which is good, no problem. Now also, once you have trained your linear regression model using the normal equation or possibly, as we will see, any other algorithm, predictions are very fast. As you saw here, all we need is, given theta hat, we just perform an inner product with any new arriving feature vector, right? So this, again, scales as OM. So we can predict in linear time. Thanks for watching. If you enjoyed this lecture, please consider subscribing to my channel, liking this video, sharing it on social media, and if you have any questions whatsoever, just leave a comment down in the comment section below. I'll make sure I'll get to it as soon as possible.